In today's class, we're going to be talking about properties of limits. In day 3, we looked at the graphical approach for limits, but today we're going to take a look at the algebraic approach, which is oftentimes the approach that we will take for this unit. So let's take a look first at properties of limits. There's a couple of properties that's important for you to know so that come time when we solve limits, it'll be a lot easier. So let's take a look at some properties of limits. So starting off, it says for any real number a, suppose that for functions f and g, they both have limits that exist at x equals to a. That's a very, very important part here. So let's start off first by talking about our first property. So the first property states the limit for k, where k is a constant, as x approaches a, is equal to k. In other words, the limit of a constant function, which I'm going to highlight here, will always be the constant value. So let me give you an example about what I mean there. So let's say the example that I give you, the limit, let's say as x approaches -2 for the constant function 6. The limit will just equal to 6 then. The second property that I've got there is the limit for x as x approaches a will equal to a. The third property there, it says the limit as x approaches a for f of x plus or minus, depending on if you're adding or subtracting, g of x. If you're adding two different functions together, when you do the properties of limits, you can actually split it up so that it's the limit of f of x plus the limit of g of x. Property number 4 basically says the limit as x approaches a for some constant c multiplied by f of x. In that case, you can actually bring the constant back out and you can look at the limit for f of x first and then multiply by the constant c. For property number 5, we've got the product of two functions. So if you're looking at the limit as x approaches a for f of x times g of x, you can actually separate it so it's the limit for f of x multiplied by the limit for g of x. Taking a look at 6, we've got the quotient of two functions and the limit. So if you're dealing with a limit that is the quotient between two functions, f of x and g of x, you can actually rewrite it so it's the limit of f of x divided by the limit of g of x, provided that the limit for g of x isn't equal to 0. And lastly, the limit for f of x raised to some exponent as x approaches a, you can actually figure out the limit for f of x first and then raise it to some exponent n. Okay, so those are the 7 properties that we're going to take a look at involving limits. And let's take a look at solving some limits algebraically. Let's take a look at example 1. So for example 1, it says the limit as x approaches 2 for 3x squared plus 4x minus 1. So in order to evaluate this limit, I'm going to break it apart using the limit laws that I had, or the properties of limits. So I'm going to start off first by rewriting the question down. So I've got the limit as x approaches 2 for 3x squared plus 4x minus 1. I'm going to break it off. Remember, the limit properties allow me to break up the addition of functions together. So technically I could break it off so it's the limit as x approaches 2 for 3x squared, and then plus the limit as x approaches 2 for 4x, and then minus the limit as x approaches 2 for 1. I kept the subtraction sign in the front there. And then you're essentially evaluating each of those limits separately, right? And again, for 2 of those limits at the beginning, you can still break them up using your limit properties. So technically speaking, I can rewrite this so it's 3 times the limit as x approaches 2 for x and then all squared plus 4 times the limit as x approaches 2 for x, and then this one just stays the same at the back. forgot the 2 there. And then this way we can solve. So I know that the limit as x approaches 2 for x is just 2. So then it just becomes 3 times 2 squared plus 4 times 2 minus 1. And then that's going to simplify to 19. Now, if you take a quick look here at the third step that I did, okay, if you take a look at the third step I did, do you essentially agree with me that we just plugged in x equals to 2? That's all we did, right? Although we did all that fancy stuff with breaking it up in terms of limit properties, at the end of the day, all we did was we plugged in x equals to 2, which is what I'm going to bring you to for our note. If your function is a polynomial function, then the limit is just plugging whatever a value that your x is approaching into your function to figure out the limit. So essentially, I didn't have to do the first 2 steps. I just had to plug 2 into my polynomial there, and then I would have gotten my limit, which is 19. So keep that in mind. For polynomial functions, to figure out the limit, all you're going to do is you're going to plug the a value that your x is approaching into your function. And that's it. All right, let's take a look at example 2. Now for example 2, we've got the same thing. It says evaluate the limit as x approaches 5 for the square root of x squared over x minus 1. We're going to break this apart again using our limit properties. So if I'm using my limit properties, I'm just going to rewrite my question out again. So I'm going to have the limit as x approaches 5 for the square root of x squared over x minus 1. Now, more importantly here, we notice that 5, if I plug that in for x, it's not going to cause us any trouble. So in this case, I'm going to do the square root of the limit as x approaches 5 for my function x squared over x minus 1. And then I'm going to break it apart again using my limit properties now. So that's going to then leave me with the square root of the limit as x approaches 5 for x squared, and then the limit as x approaches 5 for x minus 1. And so what I'm going to do now is I'm going to break apart my limits within the numerator and the denominator. So I'm going to have the square root of the limit as x approaches 5 for x all squared all over the limit as x approaches 5 for x, and then minus the limit as x approaches 5 for 1. And then I can solve each of them individually now. So that really is going to end up for us 25 over 5 minus 1, which is just going to give me 25 over 4. And if I square root everything, that's going to leave me with 5 over 4. And again, we broke this up using limit properties. But what we're recognizing here is I could have just done a straight substitution in, which is essentially what's happened here. So now that you've seen me break it up using properties of limits, later on when you start doing questions where you can just substitute the x value in, you can just do that to figure out your limit instead. You don't have to show the breaking up of the limit like I did here. Let's take a look at example 3 now. So for example 3, it says evaluate the limit as x approaches 3 for x squared minus 2x minus 3 all over x minus 3. So just like example 1 and 2, we're going to try to do now, without using those properties of limits, we're going to do a straight substitution. We're going to plug in x equals to 3 now. So I'm going to have the limit as x approaches 3 for x squared minus 2x minus 3 all over x minus 3. And if I plug in if I plug in 3, because I'm doing a straight substitution to help me find my limit now, I'm going to get 3 squared minus 2 times 3 minus 3 all over 3 minus 3. Now, when you solve the numerator, you get 0. When you solve the denominator, you also get 0. And then you're stuck with this. And then you try to plug it into your calculator to see what it equals to. And chances are your calculator told you error or math error. When this happens, when you do a substitution for whatever x value you're approaching right into your equation or right into your function, and you get 0 over 0 when you're dealing with the limit, this is not something we want to deal with. We call this an indeterminate form. And the reason why we say that is because it doesn't help us. It doesn't tell us anything about the limit. Okay, so if you do a straight substitution of your x value into the function for your limit and you get 0 over 0, that's where we run into problems. So then you're probably thinking, okay, so we ran into a problem. How can we fix this problem? What can I do so that I can potentially figure out what the limit is? Well, take a look. This is a rational function. You know some techniques to help you potentially simplify rational functions. And the first thing that should come to your mind is factoring. So we're going to do exactly that now. So let's take a new approach. We're going to do the limit as x approaches 3 for x squared minus 2x minus 3 all over x minus 3. So we're going to factor out the numerator and the denominator if possible. So my numerator is actually going to factor out to x minus 3 and then x plus 1. And then my denominator is going to give me x minus 3. Right away, I notice, hey, I can cancel something out from the numerator and from the denominator. So I'm going to do exactly that. And now we're working with a much more simplified function now, which is x plus 1. 3 is no longer an issue for us if I do straight substitution now. So I'm going to substitute it in. So if I do 3 plus 1, notice the moment that I plug my x in to help me find the limit, the words limit and x approaches 3 disappears. And then that's going to give me 4. So that means that the limit as x approaches 3 for x squared minus 2x minus 3 all over x minus 3 is 4. But we had to do a bit of work before we could get that limit. And it's all because we had an indeterminate form to begin with. So this can't be the only case that you're going to see indeterminate forms. So I'm going to give you some tips and tricks in terms of how can we solve limits algebraically if we're stuck with indeterminate form to begin with. So if you take a look at the bottom here, okay, so this should say 0 over 0, and this should say 3. So when we directly substituted 3 for my x in that previous example, we ended up getting 0 over 0, which is what we call indeterminate form, and it tells us nothing about our limit. So what we have to do is we have to use our skills that we've learned through, advanced functions, and earlier on in this unit to help us create equivalent functions, not fractions, equivalent functions that will allow us to solve the limit instead. Some ways that we can kind of get around indeterminate form, we can do things like factoring, which is what we did in the previous example. We could work with rationalization, which is what we learned in this unit. We can talk about one-sided limits. That more pertains to piecewise functions, but looking at the left side limit, looking at the right side limit. Or number 4, substitution by a change of variable. So let's take a look at all these different techniques that we can use to help us algebraically solve limits now. Let's take a look at example 4. So in this example, it says, evaluate the limit as x approaches -1 for 2x squared plus 5x plus 3 all over x plus 1. Always start off by doing a direct substitution for your x value first. If it works, then you don't have to do all of that weird stuff that we were talking about. If it doesn't, and it gives you an indeterminate form, that's when you have to think about all those different techniques instead. So if I do my work on the side here, I'm going to do the limit as x approaches -1, and I'm going to do for 2x squared plus 5x plus 3 all over x plus 1. So if I do that, I'm going to do 2 times -1 squared plus 5 times negative 1 plus 3 all over negative 1 plus 1. In that particular case, we do end up getting 0 over 0, which is the indeterminate form, which we don't like. So we're going to have to see if we can do something to make this possible. So I notice that this is very similar to example 3. So I'm going to think about, maybe I can factor here. So I'm going to do the limit as x approaches negative 1 for 2x squared plus 5x plus 3 all over x plus 1. I'm going to factor the numerator, right? So you can use crisscross, you can use decomposition. However you choose to factor, you're going to get 2x plus 3, and then you're going to get x plus 1. And then all over x plus 1. Right away, I notice, hey, I can get rid of x plus 1. And then I'm left with the limit as x approaches negative 1 for 2x plus 3 instead. Now, I notice that x equals to negative 1 doesn't cause me problems here. It won't give me an indeterminate form. So now I can do direct substitution. Remember, the moment that you substitute your x value in, you're going to drop the words limit and x approaches negative 1. So you're going to do 2 times negative 1 plus 3. And if I simplify that, that's going to give me positive 1. So the limit as x approaches negative 1 for 2x squared plus 5x plus 3 all over x plus 1 is simply 1. And we had to use factoring here to help us. Let's take a look at example 5. In example 5, it says, evaluate the limit as x approaches 0 for the square root of x plus 1 minus 1 all over x. Again, start off by doing a direct substitution first to notice whether or not you're going to get an indeterminate form. So I'm just going to do that on the side here. The limit as x approaches 0 of square root 0, missed them plugged in x when you're not supposed to here. So we're going to keep it as x first. X plus 1 and then minus 1 all over x. Now I'm going to plug in 0 for x. I'm going to get 0 plus 1 minus 1 over 0. If you simplify, you end up getting the indeterminate form, which means we need to think of another way now to see if we can solve this limit. So right away, what comes to mind is UC radicals. Chances are, if you can get rid of the radicals in the numerator spot, you might be able to solve this limit. So in this case, since I don't tell you which part to rationalize, you have to be very mindful of, does the numerator have a radical or does my denominator have a radical? In this particular case, my numerator has a radical. So I'm going to rationalize my numerator instead. So I'm going to start off with my original question as x approaches 0 for square root x plus 1 minus 1 all over 0. I'm going to then multiply by my conjugate now. And the conjugate refers to the conjugate of the numerator. That should be x at the bottom there, not 0. My apologies. So I'm going to multiply the top and the bottom by square root x plus 1 and then plus 1. Same thing here, x plus 1 and then plus 1. So once I do that, I'm going to simplify my numerator and my denominator now. So at the top, I'm going to get x plus 1 minus 1 squared all over x times the square root of x plus 1 plus 1. So in the top here, the square root of x plus 1, all squared, just leaves me with x plus 1. So if you're wondering where that square root went, I kind of got rid of the square root because of the square. And now we're going to simplify, and that's going to give me the limit as x approaches 0. The top there is going to simplify just to x over x times the square root of x plus 1 and then plus 1. I notice right away that I can cancel x's from the top and the bottom. And then I'm left with the limit as x approaches 0 for 1 over the square root of x plus 1 plus 1. At this point, after simplifying, I notice that if I plugged in x equals to 0 into my function for my limit, it's not going to cause a problem. So I'm going to do straight substitution now. So I'm going to end up getting 1 over the square root of 0 plus 1 plus 1. And if I simplify, I'm going to end up getting 1 over 2. So the limit as x approaches 0 for the square root of x plus 1 minus 1 all over x is 1/2. But we had to use rationalization, and more specifically, rationalizing the numerator to help us solve this particular question.